Okay, for bell work today. We've got a review question from that quiz. Find the sine of theta divided by 2. And then a review question from yesterday. Are these two vectors orthogonal or perpendicular? It should be the last thing you wrote down from the notes yesterday. I'll give you 4 minutes to try it on your own, and then we'll go over it, and then everyone will be happy. Okay, key part for number one here is to write that formula from your notes for 5.5. It's a half angle. Angle divided by 2. So it is plus or minus the square root of 1 minus the cosine of your angle all over 2. So to find this out, the only thing we really need is what is cosine for this angle. To find cosine, we would do adjacent over hypotenuse, right? Uh-oh, it doesn't tell me what the hypotenuse is. How can I find the hypotenuse though? Yeah, put these two numbers, 5 and 12, and I need the hypotenuse. Pythagorean theorem. 5 squared plus 12 squared is the hypotenuse squared, which gives you 25 plus 144 is 169, and the square root of 169 is 13. And so our cosine will just be 5, our adjacent, over our hypotenuse, 13. Also, we don't really need this plus or minus here because since these are the angles inside of a triangle, the angles inside of a triangle are always positive. So we can say that this is the sine of theta divided by 2 is just a positive square root of 1 minus 5 over 13 all over 2. And then we do need to simplify this. We don't like having fractions within fractions. So how do I get rid of this? Divide by 13. Multiply. Do that to every term on top and every term in the denominator, and you get the square root of 13 minus 5 over 26, which is 8 over 26, which is 4 over 13. And then I think it accepted that, but if you wanted to take this further, that's really 2 over the square root of 13. And I think it accepted that as an answer. Or if you do this for the ACT, they're not going to like that square root of 13 in the denominator and rewrite it as 2 square roots of 13 over 13. So I think either of those three it accepted. ACT is going to like that last answer the best. Generally speaking. All right, questions about number one? I will have to clear this to make room for number two. So does anybody need more time to write? Okay. Can anyone tell me what their notes say from yesterday about how whether I test or how do I test whether or not two vectors are orthogonal? Their dot product should be 0. So we're going to do u dot v and see does that equal 0. All right, so to do u dot v, we'll take 2 times 6 and add -3 times 4. And that would be what, 12 minus 12? It is 0. Look at that. So u and v are perpendicular, also known as orthogonal. Okay. All right. Today, we're going to finish out 6.4. I realized that I did not update. This should be 5. 64 was yesterday, and this should be 6.4 continued. There we go. Okay, anyway, what we're going to do today is really actually just a bunch of physics problems. We're going to apply what we learned yesterday to write two vectors or write a vector as the sum of its two components, and use vectors to find work done by a force. First example. So if you want to find the components of a vector, let's say that we have a cart sitting here on a ramp. The cart weighs 200 pounds, and the ramp is inclined at 30 degrees. What we want to find is the parallel component, W1 here, so we can know how much force is required to keep this wagon on the ramp. Or sorry, keep this cart on the ramp. We are going to assume that this is a frictionless surface. All right, to do that is actually, okay, there are two ways you could do this problem. One is by using vectors and finding the projection of one vector onto another. I don't think that's how Ms. Vignano is teaching her physics class, so I am not going to teach you that method. If you are interested, it is on page 440. Instead, I'm going to teach you the way that I think Ms. Vignano would teach you, which is really just to use trig. So I have a right triangle here, and I know that its hypotenuse, this force due to gravity, is 200 pounds. So the length on this side of the right triangle is 200. What I want to find is the parallel component here, W1. And to do that, I need an angle inside this triangle. Here is the thing that messes people up the most, and that is getting the appropriate angle. So if you extend, look, they got a line here. And if I draw a horizontal line through that, this angle right here is 30 degrees. Right? So then this angle up here is 30 degrees as well. So this angle inside the triangle is not 30 degrees. What is this angle? The angle of the ramp is 30 degrees. And if you draw your vertical angles, that means this angle outside the triangle is 30 degrees. What is this angle inside the triangle? 60. These two angles have to add up to 90. So if I redraw that triangle over here, here's what it looks like. This is 60 degrees, 90, W1. And since F is 200, I'm going to use trigonometry to find W1. W1 would be the adjacent side to 60 degrees, and 200 would be the hypotenuse. So the cosine of 60 degrees should equal W1 over 200. Which means W1 is 200 times the cosine of 60 degrees. Calculator. A 100. So if the wagon has a parallel force of 100 pounds moving along the ramp, you would need an opposite force of 100 pounds to keep it held there. Again, that assumes the ramp is frictionless. If the ramp wasn't frictionless, then you would also need to find the perpendicular component here, which we would do same thing. We would just find the opposite. So then we do the sine of 60. And then you would need to find your coefficient of static friction, right? And you multiply your normal force or that perpendicular component by your coefficient of static friction. And then you can add that to a force that's helping the wagon stay there, right? But for now, I believe for all the homework, you ignore friction. So you won't have to worry about that at all. Okay, do we feel okay about this? Questions about the cart? Question I got for first hour is what's in the cart? It's hummus. I mean, party later. Lots of hummus, 200 pounds of hummus, minus the weight of the actual, like, wheels and frame. Okay, let's have you do one then. Same problem. That's a 150-pound cart now, and the ramp is now 15 degrees. So, oop, I don't want that. Undo. So this is 15 degrees. You've got a 150-pound cart. You need to tell me what the parallel component is so that we can get the force that we would need to hold this cart on the ramp. Give you 3 minutes to try it on your own. All right. So again, the first thing you really need to find out is what is this angle right here? Oh, you already answered once. Okay, Jackson, the dice has decided it is you again. What do you think this angle is right here? It is 75 degrees. That's right. So again, the idea would be that this angle up here is 15 degrees. So then the vertical part here is 15 degrees. All right. So then how do I find the horizontal component? What do you think, Caitlin? Good question. So I want the adjacent side, given that the hypotenuse of this right triangle is 150. Which trig function can I use to relate adjacent and hypotenuse? Now, before we do that, sine, cosine, or tangent? For adjacent and hypotenuse. Cosine, yeah. And I will be honest, most of the stuff you're actually going to do for the homework is cosine. I don't know, they just really like horizontal movement problems. There's like no vertical ones that you have to worry about, but whatever. All right, so we're going to do the cosine of 75 degrees is the adjacent, which, well, I don't know, let's call x, over the hypotenuse 150, which means x is 150 times the cosine of 75 degrees. So our force parallel to the ramp then is 38.823 pounds. So that is the force that we would need to apply to stop it from rolling down the ramp, assuming no friction. If there was friction, like on your physics final that you might have to take, then all you would have to do is also find the opposite side, right, using sine. That would give you the normal force, and then multiply that by your coefficient of static friction. And then you would subtract that from this number. Because that's like the amount of work that, or I shouldn't say work, that's the amount of force that friction is applying to help keep the cart in place. Right? Pretty sure that's how you physics. All right, questions about carts? Yeah? What's in the cart? To go along with the hummus, pickles. And you dip the pickles in hummus. You eat it. You thought I was going to say pita chips, tortilla chips. No, pickles. Everyone expects pita chips. You got to surprise them with the second cart. Right? Yeah. 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 Okay. Let's talk about work. Work. The work done, I'm going to be honest, there are 3 formulas here. You only really need actually one of them, to be honest. And the one I would use is the same one you probably wrote for your physics class. Magnitude of your force times distance. That's what work is. This one might be helpful because it's, actually what you end up doing. For most of your problems, you're going to find the parallel component of your force to the direction that you're moving. And to do that, you'll usually, I should say actually always, I think for the problems we're doing, especially, and even if it's not, even if it is vertical, you can set it up so that it does work out. But you take the cosine of your angle times your force to get its parallel component, and then you're just going to multiply that by however far that force is acting on. the distance that is traveled. I need to get some more pickles. Might stop. Store. Mar. Pickles are low calorie, like 0 to 10 calorie food. All right, yay. All right, let's talk about a barn door then. So this is you right there. You have found yourself, in order to better understand pre-calculus, traveling out to a real live farm, okay, and finding a frictionless pulley system here. And you're going to close this barn door by pulling on this rope with a constant force of 50 pounds at a constant angle of 60 degrees. We want to find the work that's done to close it, which requires you to move it 12 feet. So in order to do this problem, we're going to find the magnitude of our force, our horizontal component here, or our parallel to the direction we're moving it, and then we're going to multiply that by 12. Hey, it's going. You missed both the hummus and the pickles, but you're here for the barn door, and that's what's important. All right, so find this horizontal component. I'm just going to make a right triangle. Okay. Notice that I already have the angle for this right triangle at 60 degrees. Go golly. So then if I want to find the adjacent side, it's a good color, blue, adjacent, given the hypotenuse is 50, and what we'll write is the cosine of 60 degrees is equal to x over 50. Or maybe I think a better notation would be for this problem, f sub x. Is that a notation that Ms. Mignano uses? Force in the x component. Solve that, we get 50 times the cosine of 60 is equal to your force in the x direction. Calculator is 25 pounds. And we're going to take that force and move it over a distance of 12 feet. So then the work will be 25 times 12, or 300 foot-pounds. Yay. All right, how do we feel about barn doors? Any questions about that? No? Okay. I was worried that this was going to be like the harder part of today's lesson, but I actually think this might be easier than what we did before. I don't know, maybe not. All right, last question. We've got a wagon. All right, so draw a picture. There's your wagon. Okay. Sure you get the spokes. It's important. Okay. It's pulled by a handle that's making a 30-degree angle with the horizontal with a force of 35 pounds for a total distance of 40 feet. What is the work done in pulling that wagon? Huh? All right. Have fun. He's never going to know the work done by the wagon or done to the wagon. Again, we're assuming friction doesn't exist for this wagon either. If it did, you would need to know the weight of the wagon, and then you'd have to find the vertical component of your force, subtract that from the weight, and find your coefficient of kinetic friction. That is additional. Actually, that's not true. Never mind. It just, we actually don't need to do that. Do we do that? We would. Yeah, we would. Because that coefficient of kinetic friction would be subtracted. Added to your parallel. Or maybe we did it more. So we're just finding work and not the net force. And you do work, do you do it off the net force or the like initial force? Like this 35 pounds, huh? Oh, well, never mind. Never mind. I take it all back. I'm doing too much. That's okay. All right, George. Nope. Fix this. Okay. Do you know how I could find this horizontal component here? Or the adjacent side? Yep. Over 35. So then the force, or the x component of the force would be that, which comes out to be 30.311 pounds. And then to find work, we're just going to take that and multiply by our distance, 40. So 30.311 times 40. That gets us 1,212.436 foot-pounds. And then we could like convert that to joules. right? If we wanted to. And then once you have it in joules, that tells you like how much money you get. And you can find the exchange rate of joules to like dollars, right? For Poland's wagon. And that's how currency was invented. Physics. Isn't that a good picture of a wagon? Look at that wagon. That's a good picture of a wagon here. The key part is the spokes. That's what people notice first. You'd be like, okay, that's a real wagon right there. It's got spokes. All right, what's that? 12:34. So we got 12 minutes. That was it. So you got these 12 minutes to work on homework. And then tomorrow we'll do 6.5, the complex plane, which is not too bad. It's a pretty short lesson. What are you all working on in physics now? Torque. I remember you telling me that now. Torque. Wonder if we did, I don't know. I don't think there's any torque questions I could ask you. Nope, there's no torque questions. Torque. When did you do work? Was that have been last unit? Oh, well, look at this. Never mind. I was gonna say, I could rearrange my stuff to better coincide, but I suppose it's probably better if you hear how she wants you to do it first, and then I show you this. That way it's like a reminder because they have a more particular way of how they want work shown in physics than I do. Yeah. Because you have to draw a diagram right and label things appropriately and do other stuff with the answer. That's fair. But you all didn't have any work and friction problems? Because if friction existed in this, that's fair because it does kind of mess you up a little bit because you could think the resulting force, right, is going to be affected by this kinetic friction. Right. Like this will be actually subtracted by the friction of however much this wagon weighs minus how much I'm lifting it with the handle. But I don't think that actually affects the amount of work you have done because I'm still exerting this. This is the force I'm exerting, right? Times that. So I think that's fair. I imagine the kinetic or the friction won't even matter. All right. Well, I probably should stop recording about